I'll begin. Dearly Father, we thank you for this day again, Lord. We thank you for the break, and just pray you'd help us to regain our focus for the remainder of the semester, Lord. Just do the best each day for your glory, Lord. In your name I pray. Amen. So today, talking about the wave equation, and the wave equation is, well, kind of what it sounds like. In particular, we'll start by thinking about waves on a string, but the truth of the matter is the same mathematics appears in other kinds of wave phenomena. But here it is. Suppose you have a string, all right? And suppose we just look at a little bit of it like this, perhaps, all right? So on this little bit of string, right, if you will, of course that's got some little mass, right? There's some mass m here, and so we could study the forces on that string, and we're going to assume that the forces on the string are primarily tension forces, all right? So gravity is negligible. And so then to understand it, we can study 2 points. The one point we'll study here, say x comma y, and then the other point over here would be, say, x plus delta x, y plus delta y, if you like. All right? And so we can envision the tension. What's the direction of the tension force? It's like this, right? Or over here like that, right? Tension. And so we can write Newton's second law on this little bit of, and let's also suppose that lambda is equal to the, mass per unit length, right? Let's see here. So this m, so m would be what? Something like lambda what times delta x, right? To a good approximation. Okay, so what does Newton's second law look like on this little bit of string? So we have m, and we'll look at the y component. Y component, so we have mass times what? Let's see here, d squared y dt squared, right, equals to what? Mass times y acceleration should be the net y force, right? Right? So what's going on there? What is the net y force? You have the two different tension forces here, right? And let's see here, if I drew them better. This one would be, let's see if I've drawn myself into trouble. Let me just make it fix that so you can see it better. Like that. Anyway, the point is, I'm interested in the part of the tension which is what? I mean, the y part. So I can break that into two pieces, right? I mean, there's this piece and that piece, right? And likewise over here, you can take the tension and break it up into the two different parts, right? And let's see here how to get at this. So the magnitude of both is both t, all right? That's why I use t for both. But they're different forces. They just have the same magnitude because we're assuming that the string doesn't stretch, which is to say that the tension is the same throughout the string. Okay, so great. So I need the y component of this force. How do I get that? T sine angle. Yeah, I think you're right. I mean, if I could call this theta 2, and if I was to call this theta 1 or something like that, then yeah, I'm totally on board with that. This would be t sine theta 2 minus t sine theta 1, right? But I need to somehow, I mean, that's not wrong. Totally on board with that. But I need to somehow relate it to the slope of the curve there. Now, what's the slope? Let's see here. I say this. So the slope here would be what? I need to. So right here, slope would be partial y, partial x at x plus delta x. All right. And over here, the slope of this would be partial y, partial x at x. Well, this is comma y, of course, but I'd like to use those slopes to write the y component. Now this m, this m is actually what? So this is fine. It's fine, just not what I need. So this is really lambda delta x. And that, to be more technically correct, is partial. Y is a function of two variables, right? So this is really the partial derivative with respect to time squared, to be more honest here, because we're holding x fixed there, so to speak. And let's see here, how can I write those in terms of tension and the slope? Let me draw a picture. Maybe it'll help. So this is the magnitude is here, tension, right? And we have partial y, partial x is how is it related to? Well, I mean, it's going to be the y component of the tension to the x component, right? Now, so in other words, ty is equal to tx times partial y, partial x, right? But I'm going to cheat a little bit. As long as the slope is relatively small, the tx is essentially just t, right? So to a good approximation, I can trade this for just t, the magnitude of the tension in the rope or string, times partial y, partial x where? X plus delta x, right? And then minus the tension times partial y, partial x at x comma y. So long as theta 1 and theta 2 aren't really large, those are very good approximations. And in the limit, as delta x goes to 0, those become even better. What would it mean for theta to be very large? I mean, theta to be non-zero. Like suppose theta continues to be 30 degrees as delta x goes to 0. What would that say about the string? That would mean the string has some kind of like that in it, you know, for there to be a large theta even as you shrink your delta x. As delta x shrinks, if you zoom in on any part of this string, the theta should be about the same before and after. And so, anyway, I'm going to shut up about this. So hand waving aside, okay, we have this, and then what happens when you divide by delta x? I'll put t as a constant, bring it over here. We get lambda over t, partial squared y, partial t squared equals to partial y partial x at x plus delta x, comma y plus delta y, minus partial y partial x at x comma y, all divided by delta x, right? And we consider the limit. What happens as delta x goes to 0? What does this become? You're looking at the change in the derivative with respect to x, right? With respect to x again. And so, again, with a little bit of hand waving here, but not too much, this is partial squared y, partial x squared in the limit. And so that's why the wave equation we can write as lambda over t, partial squared y, partial t squared, equals to partial squared y, partial x squared. This is the wave equation. And it really is nothing more than making some simplifying assumptions that the motion on the string is not too chaotic, so you can make these approximations. It's not too jagged a motion. If the motion gets to be too jagged, I don't think you can neglect gravity anymore, right? If the string gets kind of vertical, it's not the tension force that's dominant. All of a sudden it becomes free-falling string, right? I mean, there's the assumptions of the setup stop being true if you get too far away from where this approximation is reasonable. But anyway, we can rewrite this. Let's see here. Let's see. This is could also be written as yxx, right? Well, I'll stick with the partial notation for a second here. Partial squared y, partial x squared equals to 1 over t over lambda, partial squared y, partial t squared. So my question to you then is, what's the dimension of this quantity? What does a dimensional analysis reveal? What are the units on that? If y has meters, let's say, t has seconds, what are the units on t over lambda? Of course, you could figure it out from where it came from, right? I mean, t is a force, it's got newtons, lambda is a mass per unit length, right? So, of course, you could say, well, it's newtons over mass, kilograms over meters, right? Which is a kilogram meter per second squared. You're like, oh, man, seriously? I thought it was free from that. Let's see here. No. Wait a minute, aren't you guys mechanical engineers? What do you guys working feet in seconds? Huh. Neanderthals. Let's see here. Sorry. No. I'm sorry, we don't even believe in those. What am I talking about? Let's see here. So, where was I? Oh, yes. Looks like we've got a meter squared over second squared. Kilograms be canceling. So what is t over lambda? It is something like a speed squared, right? It's a velocity squared. And so, in fact, that's what this is. This is actually the velocity is the square root of t over lambda. This is the speed of the wave. So the speed of the wave is inversely proportional to the mass per unit length, right? So if you look at waves on a heavy chain, as that's a little bit violating some of the assumptions of this model, but a heavy cable, right? That's going to have a pretty slow wave compared to the same tension and a much lighter weight string, right? The lighter mass per unit, the less mass per unit length, the faster the wave. It says 1 over the mass density, right? On the other hand, the more tightly you stretch the string, the faster the wave propagates, right? Does this match your intuition? I hope, yeah? No one's ever played with waves on a string? You guys I should do this for a FACS class. Is there a FACS class in jump roping? No? Oh, okay. What major does jump roping here? Exercise science, right. That's right. Yeah, of course. What was I thinking? What do people in FACS study? I don't know. I know they study something. I've seen it. But, oh, okay. So, yeah, we should figure out how to solve these then, right? Sorry. I got lost in my physics for a second there. So that's a derivation of the wave equation. I didn't derive the heat equation for you because the heat equation basically just says that the temperature spreads depending on some proportionality constant, which is characteristic to the material. It's just a diffusion relation. This, on the other hand, we can derive from Newton's second law if we're so inclined. And so I was so foolish as to attempt it this semester, and there it is. You can blame Dr. Scombortis. I wasn't going to do this until he mentioned it right before class. I was like, oh, yeah, I should do that. So here it is. So, setting aside that derivation, we now face the following problem. We want to solve yxx equal to 1 over v squared ytt, right? And this is the wave equation, and aka I don't know. It bothers me to write like this, but that's our other notation, right? But understand, of course, this just means second partials, right? Fine. And we're going to solve it for 0 less than or equal to x less than or equal to L, all right? So our picture is we've got x equals to 0 here. We've got x equals to L over here, right? We've got the string between those 2 points. The only thing I insist on, my boundary conditions, are that the string has fixed endpoints, okay? That's a specialization. Of course, you could fix one of the endpoints and let the other one wiggle. You could do that, right? And you could solve that mathematically, but we're going to focus our attention on the case of fixed endpoints, both endpoints fixed. So that means that y of 0 comma t is equal to y of L comma t equals to 0 for all positive time, right? We'll think of time as being positive. And we'll start our analysis at time 0. So, you know, the wave equation is coming from Newton's second law. To solve a force problem, what do you need? If you want to actually find a specific equation to Newton's equations, what 2 things do you need? Initial what? Position and initial velocity. Same thing is true here. So to solve this, I need to know the initial shape and the initial speed of the wave. So there are 2 initial conditions here. So in particular, now given y of x comma 0 equals to, let's say, f of x, all right? And partial y, partial t, at x comma 0 is equal to g of x for 0 less than equal to x less than or equal to L. So we have boundary values, and we also have now 2 initial conditions. Our method to solve this is going to be pretty much the same as what we did for the wave equation. We're going to solve the boundary value part, and that is going to suggest for us a whole family of solutions, so-called eigensolutions, and then we'll use a Fourier technique to fit that solution to these given initial conditions using Fourier analysis. So the big picture of the solution is just the same as it was before. So let's get into it. So what's our starting point then? We assume that the solution is a product solution. In other words, that we can write y as a product so this is sort of our starting point. We'll suppose y is equal to, let's say, x of x times t of t, right? So with that in mind, we have yxx is x prime prime t, and ytt is x t prime prime. using the notation like we did last time that the primes on the functions refer to ordinary derivatives. So when we differentiate with respect to x, the t function is constant. When we differentiate with respect to t, the x function is constant. And then plug those in to the wave equation. Here v is a fixed constant. Okay. Fixed positive constant, actually. And, all right, so let's plug it in. What do we get? We get, so let's see here. So we got yxx equals to 1 over v squared ytt, right? What's that tell me? That tells me that x prime prime t is equal to 1 over v squared x t prime prime. So then what do? Same thing we did last time. We'll isolate functions of x and functions of time. And to do that, just divide by xt. So this gives me that x prime prime over x, right, is equal to t prime prime over v squared t. But I will point out to you, as I did last time that we did this, that at this stage in the calculation, this is just a function of x. This is a function of time, t. The only thing which is commonly a function of x and t is a constant, right? So constants are those boring functions which are, I give you f of stuff equals to 3. Is that a function of theta? Is it a function of time? Is it a function of space? Is it a function of temperature? Yeah. In a stupid way, 3 is a function of all those things because it has nothing to do with any of them. So this is stupid, but anyway, so we'll set this equal to minus k. The reason for doing that is, again, to link with the propositions that I went through last time, right? So with that, putting that equal to minus k, we face x prime prime plus kx equals to 0, and t prime prime plus kv squared t equals to 0, right? You understand what I did? I just solved these both for k. And the reason I put that minus there is so we get a plus when I write these equations. So again, it looks like the ones we've already thought through. What about boundary conditions? So these were the boundary conditions over here, right? These are the boundary conditions. And how do those translate? So the boundary conditions y of 0t equal to 0 and y of 0t equal to 0, y of lt equals to 0. This implies that what? This implies that x of 0 times t of t equals to 0. This implies that x of L times t of t is equal to 0, right? For t greater than 0. So the only way that those can be interesting, unless the time is identical, if the time solution is identically 0, we're not interested in that. That's the 0 solution. So to get interesting solutions, we need time to be non-zero. So to satisfy those boundary conditions, we must have that the spatial part matches the boundary conditions, right? We need that x of 0 is 0. We need that x of L is 0. So in other words, the boundary conditions, they naturally descend to the product solutions in the natural way. So we get these boundary conditions for x, right? So let's look at what we got. What do we got? We're trying to solve x prime prime plus kx equals to 0, subject to what? X of 0 is 0. X of L equals to 0. What are the solutions to that? Proposition 1, right? The thing I worked out at the start of the last class. I hurried through in a misguided attempt to give you guys time to ask me about homework. You may recall. I was fished in. Let's see here. This, by the work we did last time, implies that k has to, in fact, be equal to n squared pi squared over L squared, if I remember right, and x sub n of x is, in fact, nothing more than sine of n pi x over L. These, there's something weird on the board. I don't know what. I hit some kind of, there was like some sort of like giant clump of red marker there. It was weird. Anyway, sorry. Those are solutions to this boundary value problem. Remember, we consider three cases: k less than 0, k positive, k negative. And when you sort through that, k negative and k0 give you no solutions. Those are hyperbolic sine and cosine. And the constant solutions, none of those match the given boundary conditions. But on the other hand, k positive gives us sines and cosines. But in order for those sines and cosines to be 0 at both 0 and L, we have to take sine. And you can check that this works, right? If you plug in 0 for x, we get 0, right? What happens when you plug in L? We get sine of n pi, right? Which is 0. So you can see that this solution does, in fact, solve the boundary conditions. And if you go through the details, which we went through last time, you can see that more than that, these are the only functions which satisfy these boundary conditions. So with this, we get, great. So that's half the battle. So now we return to the t equation. What does that give us? We've got t prime prime. Now we know what k is. K is plus n squared pi squared over n squared pi squared v squared over L squared t equals to 0. Right? Now this one is not a boundary value problem. It's just a symbolic ODE. We know how to solve this. This implies that the characteristic, thinking back to the start of the course, lambda is n pi v over L, right? Times I, right? It's got a pure imaginary characteristic root, right? Because it gives you lambda squared plus n squared pi squared v squared over L squared equals to 0. That has solutions of plus or minus n pi v over L, which tells me that my solutions are like this. Tn of t are something like, let's say an cosine of n pi t. Oh, worse than that. N pi vt, n pi vt over L, right? Plus b sub n sine of n pi vt over L, right? This is kind of annoying. Maybe we should give this thing a name, yeah? Let's let omega well, let me not do that. That'll obscure things. I mean, you might want to, I could see reasons for starting to, there might be a good reason to invent a letter here, but I'll just, you know what, stay down there. You're useless anyway. So here we go. Y. So y sub n of x and t would be something like a sub n sine of n pi x over L cosine of n pi vt over L plus b sub n sine of n pi x over L sine of n pi vt over L. What does this do? This function satisfies what? The boundary conditions. That's it. This is the product solution which satisfies the boundary conditions. Now, we have initial conditions. We have an initial velocity and initial speed, initial velocity and also initial position of the string that we need to match. So the way to do that is to not use one of these, but to use all of them. And so the blank template, as I call it, this gives us blank template y equals to the sum n equals 1 to infinity of a sub n sine of n pi x over L cosine n pi vt over L plus b sub n sine of n pi x over L sine of n pi vt over L. We're expecting that appropriate choices of a sub n and b sub n will match initial conditions. All right. Ay, ay, ay. Yes?
So what is that used for? Is that just for the wave equation, or is it like for something else?
This is just for the wave equation, and we're not quite done yet. So we reached the same point with the heat equation after we got through fitting the boundary conditions. We set up the blank template, but then we had to find the coefficients, the a sub n's, using the Fourier integrals. So that's the next step. We use the blank template. There's enough freedom in there to fit these. Let me be specific. But not specific. I mean specific, but in the same time not, because I didn't give you specific f or g here. I will project one with specific formulas in it once I get through this, but it's important to not be distracted by the formulas because there's a general thought pattern here I need to communicate before we get distracted by the specific Fourier decomposition of the f or the g. So let's call this 1 and 2. So from 1 on blank template, what's it give me? It gives me that the sum n equals 1 to infinity. So let's think about it. What happens when we put t equals to 0 into this formula? What happens when we put t equals 0? It's okay. I have to give him a hard time sometimes. Anyway, so if we put t equals 0 into here, this is gone, right? But on the other hand, t equals 0 here puts cosine term to 1. And what are we left with? Just the a sub n sine, right? So if we put t equals to 0, we get a sub n sine of n pi x over L equals to what? Well, the given initial position. Right? But we know, as I talked about last time, we can use the Fourier decomposition, right? We can write this as the sum over, little a sub n, let's say, sine of n pi x over L, right? N equals 1 to infinity, where these are given by the little a sub n is equal to, what is it, 2 over L, integral from 0 to L of f of x, sine of n pi x over L, right? We derived that last time by multiplying both sides of the expression by sine and integrating both sides, noticing that sine of differing arguments are automatically 0 when integrated over such a region. Only the matching term survives and somehow gives us that 2 over L. We derived this Fourier integral last time, but the same math holds here. It's the same trick, same decomposition of a function as a sum of sines, a trigonometric series. And then, so what's the relation between the big a sub n and the little a sub n? What are you going to choose? I think it's pretty clear. Choose a sub n equal to a sub n, right? Which is calculated. Like this. Like this, yes. The point is you're given initial condition function, initial position function, so you can plug it into this and do this integration. It's horrible, but you can do it. In so doing, you find out what the big a sub n's have to be. We good? The idea? Okay. Then that still leaves us with 2. 2, we got, use the blank template. Now here I'm going to actually go ahead and do what is partial y, partial t of the blank template. I'll write this down before I evaluate it. If we partial differentiate this with respect to time, what happens? Of course, you've got your a sub n terms, right? You got like a sub n sine of n pi x over L times n pi v over L, right? Really minus n pi v over L cosine of n pi vt over L, right? Oh, I can't do math. What's the derivative of cosine with respect to time there? I got my minus, but I forgot derivative of sine is minus cosine, right? Okay. You guys follow? So minus sine. Chain rule brings out the n pi v over L. And then on the other hand, the second piece, I get a cosine there. Second piece here, plus b sub n, again, the sine n pi x over L, right? And then and then I get a n pi v over L, right? Times the cosine of n pi vt over L. So all I'm doing right now is I'm differentiating the blank template solution so you can appreciate how it is that we have to apply the initial velocity, right? So what is partial y, partial t at x0 actually look like in terms of the blank template? Notice that the a sub n terms are gone now. See, because now the a sub n's are multiplied by a sine, which when we plug in 0 gives us 0, right? So the term we already have control over is gone, right? And what happens when we plug in times 0 into cosine? Well, that's just 1, right? But we get something new. We get this, right? We get n pi v over L, big B sub n, sine of n pi x over L. Did you guys follow? Okay. Now what's that equal to? That's equal to, it's given to be equal to g of x. This is given in the problem statement. It's the given initial velocity of the wave. So what do? We find the Fourier decomposition of g, right? We decompose g as being equal to, let's say, the sum, I'll use a little b sub n, sine of n pi x over L, right, n equals 1 to infinity, where b sub n is 2 over L, the integral from 0 to L of g of x, sine of n pi x over L dx. Why is there a g there? Because I'm finding the trigonometric series which represents g of x. This will have different coefficients than the f of x usually, because g of x will not be the same thing. Yes? There's a constant? We're getting there. So we want these to match, right? So your question of what happens to the constant is that is actually a very good question. So notice that I'm not saying that this is logically equal to, I'm not changing this to be that. I am using the Fourier technique to take this given g and express it as a trigonometric series. This is divorced from this stuff over here. This is just a separate, it's like finding the power series for a function or something. It's something we can do independent of the statement of the problem. You give me a function x, I can find a Fourier series for x, right? But then getting back to your question, they are related though, because we want these to match, right? So to make them, this time we won't just set an equal to bn. This time we're going to do what? We want this to match up with this. See that these two series are only equal if their coefficients match term by term. Just like two power series are only equal if their coefficients match order by order by order. Two Fourier series match if they have the same kind of series set up. In other words, they're both sines, and also their coefficients at each order match, because sines are linearly independent. But anyway, more to the point, we're going to choose, remember it's the big B sub n we don't know yet, we're going to choose big B sub n equal to L little b sub n divided by n pi v. Right? Because that's what I get from solving. What I do, I just solved n pi v, big B sub n, over L equal to little b sub n. Again, little b sub n I calculate from the given g, but the big B sub n I'm trying to construct, right? Does this make sense? I hope. Yeah. See if I can find an example with Thanks. Eventually this thing will, yeah, I think that's where we give it a Give it a few minutes, it'll eventually wake up. So here's a wave equation. This one is particularly nice because the speed is 1. So those v's will just be 1 in this one, right? And also L is 1. So, you know, the division by L, the multiplication by v, they're kind of hard to see in this example. But here's your initial position, x times 1 minus x. And my initial velocity is sine of 7 pi x, right? So we already went through all this in general, all right? So eventually I work my way to the blank templates down here, actually. I wasn't calling it then. I've started calling it the blank template for about 2 years now, just to give it a name. But here it is, the blank template. And then if I plug in 0, of course this piece goes away. We're left with a sub n sine of n pi x. That has to be equal to x minus x squared, right? On the other hand, partial u partial t has to be equal to 7. Now, see, this is easier, right? Like this, you do not need Fourier integrals to do this. Well, you guys can tell me. Which b are 0? Anything except for 7 is 0, right? And b sub 7 is going to be equal to, apparently, 1 over 7 pi. Because we get 7 pi times b sub 7 is equal to 1. So I can just look at this and tell you that b sub 7 is going to be 1 over 7 pi. And all the other b's are 0. I don't need to do integration to see that. But the other one, yeah. So yeah, I got to calculate so this is integral from 0 to L. This is 2 over L, but the L is 1. So that's what 2 over L looks like here. And I'm integrating f of x times sine of n pi x over L, but L is 1. And so you got to do this integral, which looks like this, and get you to that. And then I will continue the integration over. So finishing my squiggle 1, it works out to this. And then that cancels with another piece and leaves me just that. And so after a little bit of work, I finally come to the nice, tidy formula that the a sub n's are 0 if n is even, and they're 8 over n pi cubed if n is odd. So then I can go back, and now I have the Fourier decomposition of my initial position for the wave, right? And then I'm going to basically make these the a sub, this will be the a sub 2k minus 1, if you will. So a sub 2k minus 1 is that coefficient, going back to what I have just covered up with the projector. And we build the solution, right? This is that one that one errant b sub 7 term out on its lonesome, right? And here's the n equals 7 from b term, and here's the infinitely many terms you need from odd a sub n's to build the solution to this wave equation. Yes? So there it is. And this is kind of a typical solution. It's this infinite series of products of sines and cosines. Now, 3 pages. Now, I have made your life easier because I have taken pains to condense the first part of this. You notice that if you pay attention to what I've done in the notes for you guys, I have basically provided you 4 propositions on homogeneous boundary conditions which tell you how this goes. So you don't actually have to go through these 3 cases, right? Like when I see this one, I already know that it's going to only be the this case that matters for this problem. And I'm a little worried that my k here may not be I don't think that's the same k. I think oh, look at that. Isn't that unfortunate? Notice that my k here is not matching the k I was using today. Because I have learned, excuse me very much. I have learned since I first wrote this solution that if I put a minus before, it makes this a plus, which is just more natural. So this is a self-contained derivation, in my defense, but it doesn't match my current usage of quote-unquote k. All right? Yeah.
So if you switch the minus and plus like you did, the only one we really care about is when k is positive?
Right. I mean, so because k is replaced with minus k, k negative is the case we care about here, but when I put for us, it was k positive. Yeah.
Two derivations of the same result, it's just that it's...
Exactly. Yeah. Here's another one. Actually, this one's a lot different. This number 13, solve the wave equation, not on a finite interval, but from minus infinity to infinity for positive time, given that u of x0 is 0, while partial u partial t is cosine x. And so here, I use something called D'Alembert's solution. D'Alembert's solution says that solution of the wave equation from minus infinity to infinity can be written as the sum of a left-moving and right-moving wave. This is the right-moving wave. This is the left-moving wave. Both have speed alpha. And so you can just basically work with this template. And so, I mean, plugging in this gives us that a of x plus b of x is 0, which is a of x is minus b of x. Partial u partial t being 0 on this gives me that that's cosine. So I get that minus 2 alpha b prime of x is cosine of x. But this is an ODE, which we can solve by integration to get that. But then by algebraically, a of x is that. And so you put it, that tells me a of x and b of x. Then you go back and replace x with x plus alpha t, or x minus alpha t, according to D'Alembert's solution. And that gives you this solution. Notice that this is not for a string on a finite interval. It's on the whole real line. And there's the solution like that. I don't think I assigned you guys. Well, I don't know. It remains to be seen whether or not I'll assign you one of those, right? Here's one. This is another D'Alembert. It's not what I'm looking for at the moment. I think I might have more in the notes. Let me look. Let's see, here's one. I'm given ytt is equal to 4yxx for 0 less than x less than pi. So here L is equal to pi. And I'm given fixed endpoints, all right? Initial condition of x squared times pi minus x, and the initial speed is just 0. That's nice. That means that the b sub n's are 0, right? And the a sub n's are all we have to worry about. So basically, we find the blank template. This time, notice that what's the speed here? Speed is 2, because I got a 4, which is 2 squared. So I've got v equals 2, L equals pi. The beta, I forget what my beta is. I think, well, I'd have to read my notes again. I think my beta might be, I was tempted to label something over there. I think the thing I was going to label would have been the beta. I believe beta is the thing that multiplies t. Like we've got cosine beta t, sine beta t. Yeah, look, so sine of 2nt, cosine 2nt. So I'm using beta for the angular frequency of the solution, all right? Anyway, these are 0 because the initial speed is 0. Initial velocity is 0, rather. And to get the a sub n's, I have to find the Fourier decomposition of x squared times pi minus x, which means I have to do that integral. All right? So after a half page of integration, you get this. Once you have that, you put it back in, and there's your solution. So I've actually had, you guys typically pretty much ace these problems when I give them to you in a take-home format. And I don't think it's because people are cheating. I think you guys actually understand this pretty well after we've had these talks, because it is just a culmination of things we've done. And if I attach enough points to it, you take it seriously. So you guys can do these things outside time pressure when you can work together, which is the nature of your PDE project. right? Hmm?
It's kind of like the last one.
Yeah, it's the last hurrah. After your test, there is a PDE project worth 100 points, which is due. It's been in the syllabus from the start. It's not like it's not something I've like. It's not like a secret. Actually, I could write my deepest and darkest secrets in my syllabus. It would be the safest place to write them. But now this is how you can take these problems and put them on a final exam. It's not that funny, but anyway. What kind of laugh is that? I feel like I should go out and mock him for his laugh, but get a real laugh. Shut up. Anyway, so this time the initial position and the initial velocity are actually given as sign series. So I don't have to Fourier decompose the functions. They're already given as Fourier decompositions. So I can just go straight to the blank template, right? And I can just match this. From this, I can see that A1 is 1 and A sub 4 is 13. And all the other A's are 0. So I got n equals to 1 and n equals to 4 for the A terms. And the B terms, I've got the fifth one is non-zero. But remember, I got to be careful because I have to write it down. I can't do that in my head. I can do the A's in my head because it's just matching, right? But the B's, you got to think about like I said, A sub 1 is 1, A sub 4 is 13 from matching these. But this, you see, I gotta match 7 sine 5x with 2n b sub n. So it's clear enough that I'm looking at n equals to 5 as the only non-zero one. But n equals 5 gives me 10 b sub 5 equals to 7, which tells me that b sub 5 is 7 over 10. So there you go. I've got this term, and that term. That's all that survives of the whole blank template. And these three terms will solve the wave equation. So if I give you friendly, very friendly, initial position and initial velocity, it actually makes a question which is reasonable for your final.
So these
But
are on the test.
they could be on the final.
Well, but not on the test that we're
They would not be on the test, no, because the PDE project is due after your test. So I don't really expect this to entirely settle in until you're done working out the project. Only then will you really entirely appreciate what I'm telling you right now.
So we need to worry about the partial differential equations on the test.
No, partial differential equations are not on the test, in-class test. But I will probably ask a token PDE type question on the final. It could be something like this. It could be something like actually working out the thing I hurried through at the start of last class. Actually, here's not actually a PDE problem, but a boundary value problem. Here's a boundary value problem. Find all possible solutions to it. That's a very, very possible final exam question, which, by the way, you could have solved with previous methods in the course. And trigonometry you may or may not remember. Hey. Anyway, so that brings us to Laplace's equation, which I will talk about next time. So in the time that remains, I actually want to show you something rather different. Let's see here. So suppose you got a wave on a string, all right, and it goes on and on, right? And we are given this. We're given, y of 0, t is equal to, let's say f of t, all right? And so you can think about some guy there kind of wagging the string up and down, right? And then what's the wave equation? I just erased it. I forgot it already. Oh no. Partial squared y partial t squared, right, equals to 1 over v squared partial squared y partial t squared, right?